So in this diagram, we are showing different various kinds of thermodynamic processes. So here we have showing 4 different processes for a constant amount of an ideal gas, and all of them are starting at state A. So this is starting state A, and of course this is your PV diagram. So let's talk one by one. So let's say we have first process is first process is called adiabatic. Adiabatic. So in this adiabatic process, no heat is transferred into or out of the system, right? That means Q is equal to 0, and if you remember the first law of thermodynamics, Q is equal to delta E internal plus work done by, so delta E internal is equal to negative W because Q is 0, right? So we can talk of a couple of conditions here. If W, work done by the gas, is positive, then we know from that equation that change in internal energy will be negative, right? And so internal energy increases. In many systems, a decrease in internal energy is accompanied by a drop in temperature. Example, opening a bottle of champagne, right? B is if W, work done by the gas, is negative, then internal energy will be positive. And this is example could be compression stroke in an internal combustion engine, where work is negative, and then the internal energy of the internal combustion engine increases. Great. All right, second process is called isochoric process. This is a process where there is no change in volume. So we know the work is area under the PV diagram, right? When there's a change in volume, right? So that means work done by the gas is 0. And then I can use this law of thermodynamics. That means Q is equal to change in the internal energy of the system. The third process is called isobaric process, and this is a process where pressure does not change. So this is a constant pressure process, right? So pressure is constant pressure process, all right? And so here we know work will be P times V final minus V initial because it's a constant process. So Q will be equal to delta E internal plus W, and W will be given by that formula. An example could be the boiling water at a constant pressure, right? So here is the diagram. We see that this is an isobaric where my pressure is constant. This is my isochoric where my volume is constant, and adiabatic is where this is so rapid that there's no exchange of energy. So this number one is adiabatic, and we'll talk this one, which is isothermal process. And in isothermal process, the temperature is constant. So let me go to the next slide. And the fourth process is called isothermal process. So isothermal process, and in this process, this is a process where temperature does not change. So it is a constant temperature process, right? Okay. So any heat flow into or out of the system must occur slowly so that thermal equilibrium is maintained, right? So here also Q will be equal to delta E internal plus work done, delta E internal plus so if you look at this graph here, the isothermal process is little slower than adiabatic process. Adiabatic is very fast, or is very fast compared to the isothermal process. These lines have names. For example, this adiabatic process line, that's called adiabate. This one is called isotherm. This is called isocore, and this is called isobar, right? So if you want, I can write it down. So these lines, they're called isobars, where the pressure is same, or isotherms, where the temperature is same, or adiabate, which is fast and no heat is exchanged, or the last one is isocore and isocores. Right, so these are different lines. I have different names there. Great, good.